What is the structure of a compound that has a molecular formula of C5H10O2 and has the following proton NMR spectrum? First, calculate the index of hydrogen deficiency to determine if the molecule has any pi bonds or rings. Step 1. Calculate the number of hydrogens as if the unknown was an acyclic saturated hydrocarbon that has the general formula of CnH2n plus 2. Since n is equal to 5, the unknown molecule, if saturated, would have a molecular formula of C5H12. Step 2. Correct for oxygens. Since oxygens do not change the number of hydrogens for an acyclic saturated hydrocarbon, no change is needed for the saturated molecular formula. Step 3. Calculate the index of hydrogen deficiency by taking the number of hydrogens for a saturated C5 hydrocarbon and subtracting the number of hydrogens that the unknown C5 compound has. Then divide by 2. This gives a value of 1. The unknown therefore has one double bond or one ring. What are the possibilities? The unknown has 2 oxygens, so it could be a combination of alcohols or ethers, with one double bond or one ring, or even a cyclic ether. What if there was a pi bond between a carbon and an oxygen? The molecule could have a ketone or aldehyde function group, or could be a carboxylic acid or ester. At this point, it would be great to have an IR spectrum that would help you identify the functional groups. But don't worry, the chemical shifts in the NMR spectrum provides very useful information. We can use table 17.20 to help us determine what the protons are bonded to. First, look at the most shielded peak at 4.9 ppm. From the table, we can see that the peak could be from an amine, alcohol, alkene, alkyl halides, or protons adjacent to an oxygen. This seems like a lot of different compounds, but since the peak is broad, and the unknown does not possess a nitrogen atom, the peak is most likely due to an alcohol. Now let's look at the peak at 4.69 ppm. From the table, we see again that the peak could be from an amine, alcohol, alkene, alkyl halide, or protons adjacent to an oxygen. Since the peak is sharp, it is most likely not a proton bonded to an alcohol. Thus, it could be protons from an alkene, or hydrogens bonded to a carbon, which is bonded to an oxygen. The unknown is not an aldehyde or carboxylic acid, because we would see peaks above 9 ppm. Now consider the peak at 2.56 ppm. This peak could be from protons adjacent to a carbonyl group, or an alkene. The unknown cannot be an alkyne because the index of hydrogen deficiency is 1, nor can it be a sulfur or nitrogen containing compound because these elements are not in the unknown's molecular formula. The unknown cannot have hydrogens adjacent to an aromatic ring because we do not observe peaks from an aromatic ring that would have peaks above 7 ppm. The peak at 1.04 ppm is due to protons on a hydrocarbon chain. Now let's look at the integration and splitting pattern. Integration of the area under the peaks yields the relative number of equivalent protons, giving rise to the signal. The relative ratio is 1 to 2 to 1 to 6. Since the unknown has 10 protons, integration equals the number of protons produced by each peak. The peak at 4.91 is a singlet produced by an alcohol functional group. The peak at 4.69 could either be produced by an alkene or protons bonded to a carbon adjacent to an oxygen. This peak is a singlet, which means the 2 protons are not adjacent to a carbon with protons. This rules out the alkene because geminal protons are not equivalent and would show splitting. Thus the unknown is not an alkene. The peak at 2.56 ppm is split 7 times. This is called a septet. Thus 1 proton is coupled to 6 adjacent protons. The most common way this occurs is a proton coupling with 2 equivalent methyl groups. The peak at 1.04 ppm is a doublet. Thus these 6 chemically equivalent protons are coupling with 1 adjacent proton. The most common way this occurs is two equivalent methyl groups coupling with a proton. When we write out the potential structures, we see that these two fragments must be bonded to each other. Since the peak at 4.69 is a singlet, the oxygen could be bonded to a secondary carbon, which is then bonded to the alcohol group. Is this correct? No, this is not correct. Let's check the structure. It doesn't have a pi bond, and it only has 4 carbons. This is not the correct structure. What have we missed? If this was the correct structure, we would expect the hydrogen on the secondary carbon to be deshielded more and be around 4 ppm. Let's go back to the table. The hydrogens at 2.56 are most likely beside a carbonyl group. The carbonyl carbon does not have protons and does not show up on the proton NMR. It would show up on a C13 NMR, but not the proton NMR. Let's go back. We know the peak at 4.69 is not adjacent to a carbon with protons. So maybe the carbonyl group is in between the CH2 carbon and the secondary carbon. This would add the double bond that we calculated in the index of hydrogen deficiency and the carbon needed for the correct molecular formula. Now combine the last 2 fragments and we obtain our unknown compound, 1-hydroxy-3-methylbutane 2-one. In this spectrum, we observe no coupling between the alcohol's proton and the adjacent CH2 group.